Hello and welcome back. In this particular chapter, we're going to start talking about transition metals and coordination compounds. We're only covering a little bit of this, so it's not everything about this topic. If you want to get into everything about this topic, you'll probably end up taking an inorganic chemistry class as you continue in your chemistry career. But if you're not in that one, we're just going to be covering a few things about these kind of compounds. So we're going to talk about the transition metals, a little bit about some of the trends that you see on the periodic table in transition metals. They're a little bit funkier than some of the other things. Most of the other things we've talked about have just been the alkali metals, the alkaline earth metals, and also the non-metals, because the trends are a little clearer there, but we're going to talk about them in the transition metals as well. We're going to talk about coordination compounds, what they are, and all sorts of things about how we can rearrange molecules, and talk about the different types of isomers that we form there. And lastly, we talk about crystal field theory, which is this understanding of what happens when all these things come and bond to metals. What actually happens to the electrons and the orbitals in that metal? And some funny, interesting things happen that really explain a lot about what's going on in these kind of compounds. So let's go ahead and get started. First, one of the best definitions I ever heard of chemistry came from one of my college instructors, and hi, Professor Van Hickey. And he said this. He said that chemistry is a systematic study of exceptions to rules. So we have all these rules, and they generally do a pretty good job of saying, hey, this is what's going to go on, this is what's going to go on, this is what's going to go on. But there's also this list of exceptions always. So, right, we have these rules, we have these generalized things, but there's always, always, always exceptions. And the filling of the d orbitals in the transition metals is no exception to the rule of exceptions. If we look at it, we start with scandium, the first transition metal. And it does what we'd expect. We fill up the 4s first, because remember, when you're filling in the periodic table, what you're always going to do is you're going to start filling just from the left-hand side. So we're going to do potassium, calcium, then scandium. So we're going to do the 4s 1 for potassium, 4s2 for calcium, and then we add the 3d1. And if you remember, the 3d1, right, we always do d as row number -1, and that just comes from all those calculations they did about how those energy levels come about. We're not going to go into any detail of that right now. But anyway, as we continue to add electrons, the Aufbau principle just says keep adding them in. And we go, okay, titanium's got 2. It's the second one in the transition metal, so it's got 3d2. Vanadium, 3d3. Then chromium, you'd think 3d4, but it doesn't. This is one of our exceptions to the rules. And you've probably seen this before, that chromium will borrow an electron from the 4s orbital and transfer it over to the 3d orbital. Why? Because half-filled orbitals have some stability to them. There's an energetic favorability to being half full. And the energetic favorability is enough to split up those paired electrons in chromium and stick them over there in the 3d. But then manganese, we can put that other electron back in there, and we get the paired electron here in manganese. And then we continue on kind of as we expect. Now we're going to start pairing up electrons. Remember, we don't pair to begin with, because pairing has an energy cost associated with it, right? You're putting 2 electrons kind of close together. There's an energy cost. So we have unpaired electrons first, and then we pair electrons only if we need to. And that's going to be important later when we talk about crystal field theory. So we pair up when we get to iron, which has the 6d electrons. You've got to pair it because there's only 5d orbitals. Cobalt, nickel. And then again, you see copper. You've got this exception to the rule where copper borrows one from the 4s orbital and then uses that in order to fill the 3d. And a full orbital has a lot of energetic stability. How do we know that? Look at all the noble gases. What do the noble gases do? Absolutely nothing. I mean, we can force them to do chemistry, but on their own, they don't do any chemistry. Why? Because their orbitals are full. They're happy, happy, happy. So copper will borrow one. So the configuration copper is going to be the 4s1 and the 3d10, and then zinc adds that one back in and has just kind of full orbitals. So you can imagine that zinc is probably relatively stable, and it is a relatively stable metal. So those are our rules for how we fill the orbitals. Now what we're going to be talking about here is how do we empty out those orbitals. So you'll notice we always filled the 4s first, right? And then we started adding to the 3d with our couple exceptions here. And, oops, sorry. Let me circle the actual exception. A couple exceptions here for the chromium and the copper, where we borrowed in order to get some energetic advantage. But it turns out when we remove electrons to make positive ions, we're always going to remove from the highest n first. Remember, n is the principal quantum number, 4 in the 4s, 3 in the 3d. So even though we filled the 4s first, and then say for titanium, we filled the 4s first, then we filled those 3ds. If we're going to make a charged titanium, let's say titanium 2+, the things we're going to remove first are the highest n. So we're actually going to remove these 4s electrons before we remove the 3d electrons. And this just has to do with the energetics of partially filled or filled orbitals versus the energetics of empty orbitals. As you stick those electrons in there, as you're building up these molecules, you actually change the levels of the orbitals. And so there is this change about how they come off. And they always come off with the highest n first. So titanium is going to, let's show our periodic table again. Titanium is going to look a lot like argon. Right? That's our last noble gas if we do our shorthand configurations. So we've got argon, and then we don't have any 4s's, so I'm going to go ahead and write 4s0 here. Now, 4s0 is optional. You don't have to write it, but I'm just doing it here for real clarity. And then we still have our 3d2. So we don't take any electrons from the d's. We just take them from the 4s's. And that's for our titanium 2+. So always remove from the highest n first. And this goes for just about any system. We always remove the highest n first. So, excuse me. How about for, let's say, manganese? What are we going to do? Manganese, if we do manganese 3+, so we remove 3 electrons from a manganese, it's also going to look like argon. It's going to have a 4s0, but let's choose not to write this time. Normally, manganese has 5d electrons, but we're going to take another one away. Why? Because we need a 3+ total. We need to remove 3 electrons. So remove the 2 from the 4s, and remove the 1 from the 3d. So just remember that when we add, we always add in order of the periodic table. You just follow it left to right. We add the 4s before the 3d. But when we remove, you always remove the highest n first. And so we're going to remove the 4s before we remove the 3d, even though that's not the fill order. So that's just an important thing. All right. So let's look at a few trends in the periodic table. If you remember, as you go across the periodic table, what happens to atomic size? As you go across the periodic table, atomic size generally decreases. And you mostly see that trend in the transition metals. You can kind of see that as you go across, the size decreases, but then you're going to get this increase towards the end. We're not going to cover the part of that increase too much. We're going to mainly talk about the trends between rows. So you can see the blue line here is the first row, the second row is the red, and the third row is the green. So let's just pick kind of a random element here. Let's pick the 7th element of the transition metals. And if you go over to a periodic table, what's going to be the 7th transition metal? We just count across. And so we got scandium, titanium, vanadium, chromium, manganese, iron. Oh, that would be cobalt as our 7th one, but it doesn't really matter. So cobalt, let's look at the first row. Cobalt has an atomic radius of about 125 picometers. And then we go to the second row. So below cobalt is rhenium, and then iridium below that. So when we go from cobalt to rhenium, then we go from about 125 picometers to, roughly 135, 140 picometers, somewhere around there. So there's this big jump in radius, which is totally what we expect. If you remember from the periodic table, as we went down a row, going from lithium to sodium, potassium, we always expected size to increase quite a lot because we were adding new electrons, right? Lithium, its outermost electron was a 2s. Sodium, its outermost electron was a 3s. And those principal quantum numbers were not only energy, but they were also related to size. The larger the quantum number, the larger the size. So we expect to see that in the transition metals as well, and we do, right? From first row to second row, big jump in overall size. However, from the second row to the third row, while it varies a little bit, you can see sometimes it's a little higher, sometimes it's a little smaller, in general, there's not a huge change in size going from the second row, going from the rhenium to the third row, the iridium. And why is that? What is going on that's different going from the first row to the second row versus the second row to the third row. There's got to be something different because there's this difference in trends. And if we go back to our periodic table, we look at atomic numbers. The atomic number of cobalt is 27, rhenium is 45. If you subtract those, you should get something around 18, right? Because if you count across, there's 18. How about if we go from rhenium to iridium, 45 to 77? That's a whole lot more than 18. Why is there a whole lot more than 18? Well, if you remember, we have those things called the lanthanides and the actinides at the bottom, those big, long ones. And it turns out they actually belong in the middle of the periodic table. You should actually have a periodic table that's really, really wide, but we shove them on the bottom just to make periodic tables fit on a regular sheet of paper. But really, we actually, in order to go from rhenium to iridium, we actually have to go through all the lanthanide series, the lanthanum, the cerium, the praseodymium, and all those ones in there. So going from rhenium down to iridium, there's actually a huge number of protons, an extra 14 protons that we're adding into our nucleus. And what do those protons do? Well, those protons are positively charged. You've got a negatively charged electron out here. You got a bunch of positive charges. What's these electrons going to do? They're going to get sucked in towards it, right? They're going to pull themselves in. So that first row to second row, we're adding 18 protons. So yes, they get sucked in a little, but you're in this bigger N, and overall the bigger N wins. That's why we get this large change from the first row to the second row. However, from the second row to the third row, we also have this change in N where it should be getting bigger, but we also have these 14 additional protons that are being added from the lanthanide series. And it turns out they roughly cancel out. And the bigger we get from the bigger N is canceled out by the smaller we get from having all those extra protons in the middle sucking those electrons in. And so your second row to third row atomic radius doesn't change all that much. And this second row to third row change we call the lanthanide contraction. And it just comes from those F block elements. Because we have to go through the F block going from the second row to the third row, we're adding all those extra protons, sucking in those electrons. And so there's this cancellation. There's the bigger from the bigger N, which is there every time, but there's the smaller from those 14 extra electrons, and they essentially cancel out. All right, so what I'd like you to be able to do is explain the lanthanide contraction if I ask, and I can ask in various ways, but that's essentially what you need to be able to do is why is there this difference in trend? But this difference in trend doesn't just stop at atomic radius, it stops nowhere. It continues on, is what I meant to say, to ionization energy. Now, what is ionization energy? If you remember what ionization energy is, if you come in and there's an atom there, and you say, hi, I would like to steal one of your electrons. Okay, if you must, okay, which electron would you like to steal? So I'm lazy, I'd like to steal the easiest one, please. That's ionization energy. How much energy does it take me to take the easiest electron away from an atom? Now, there's a bunch of harder electrons, right? If I've got a big atom and I try to take its 1s electrons, I'm pulling those from right next to this nucleus, this huge nucleus, right? If I've got something really far down on the periodic table, tons and tons of protons, it's going to take me tons of energy. But if I'm trying to pull out one of the far away electrons, right, it's not too hard because it's really far away from that nucleus. So we get those trends in ionization energy on the regular parts of the periodic table, where as you go down, because the atom's getting bigger and bigger and bigger and bigger, you get a smaller ionization energy. It's easier to take electrons away from a big atom, right? Because they're so far from the nucleus, they're like, yeah, fine, if you go ahead and take me, I'll be okay, right? It's still hard, right? You still have to pull it away from this positively charged nucleus, but it's not that difficult. As we go across the periodic table, if you remember the general trend, we get smaller as we go across the periodic table. Those electrons are closer to the nucleus, so they get a little bit harder to pull off. And so as you go across the periodic table in the nonmetals, you generally got a larger ionization energy, and it was related to size there. So let's look at what happens in our transition metals. Well, remember there's that lanthanide contraction, which does something funny, and let's look at what the funny is this time. You look at the first row and the second row. What do you notice about their ionization energies? Sometimes first row is higher, sometimes second row is higher. If we average out that trend, they're roughly equal. So first row to second row, roughly equal, right? So why is that? Okay, keep thinking about it. How about going from the second row to the third row? big jump. It's really hard to take an electron away from that third row one. Why does it get harder even though we're going down the periodic table? Well, remember, what happens as we go down the periodic table, we are making it bigger. We are also adding more protons. So you have to think about both of these things whenever you're thinking about these trends in atomic size and atomic or in ionization energy. We are doing two things. We are making it bigger by going down the periodic table. We are also adding more protons by going down the periodic table. And it's the balance of those that's always going to explain these phenomenon. So what must be happening here based on our data? First row to second row, we're making it bigger, and we're adding 18 protons, and those roughly balance out. And it's just as easy to remove an electron from cobalt, say, as it is from iridium. But as we go down the periodic table, what do we have? Our size doesn't change much. You remember there was this balance out between size and the charge and the size increase. And so our size doesn't change much. We get that lanthanide contraction because of all those extra protons there. But what do all those extra protons do? They're holding onto those electrons a little tighter, making it harder to remove them. Those 14 extra protons from the lanthanide series makes it so our ionization energy jumps up a lot. We want to remove that outer electron. We've got 14 more protons pulling on it, and so it's going to be harder. And so these third row ionization energies are much larger for the same reason, because of the presence of the lanthanides and their numerous protons. So in this case, the protons win over the size. Right? We don't get much change in size, but we do get the change in protons, and so it's harder to remove those electrons. All right. Electronegativity. What is electronegativity? Remember, electronegativity is the tendency to draw electrons to itself. Fluorine being the most electronegative thing on the periodic table, it loves to draw electrons to itself. Lithium being very electropositive, it loves to give away electrons. All of the transition metals have these electronegativities. You can kind of see there's this trend as you go across, they kind of increase. But again, we're looking row to row here versus across the periodic table. What do we see? Big jump between the first row and the second row. Pretty much equal between the second row and the third row. Again, you can find examples where it's one and then the other, but that's the general trend. So first row to second row. First row, they don't like to grab electrons to itself. They're not very electronegative. Second row, very electronegative. That's right. What does that mean? It likes to hold on to the electrons. What do we see in terms of size? Right? In terms of size, we saw that it got much bigger. Right? That first row to second row, there was a big change in size. But in terms of electronegativity, there's also a big change. Yes, I'm happy to hold on to electrons. But from the second row to the third row, there isn't much change going on. Okay? So what do we have? The second row and the third row, large change in protons, small change in size. Okay? Roughly balance out, and they say the second row and third row, they're about as equal. But that first row things, they're a little smaller, right? Because they haven't grown so much. But they also don't have very many protons. And in this case, the protons win. Right? Not very many protons means these guys aren't really good at drawing electrons into themselves. This one's definitely a little harder to understand, so don't worry too much if the electronegativity one's kind of a little shaky. It's always that balance between the size and the charge. Size, charge. I think personally, ionization energy and atomic size are a little easier to understand. Right? This one, if I didn't give you this data, you probably could argue it either way. Okay, and that's the kind of the fun thing in chemistry is we can argue something, and then somebody showed us data, and we're like, oh, we were totally wrong. Let's argue exactly the opposite. And that's frustrating for some people too. I totally understand that one. Okay, but I would focus, if I were you, thinking more about atomic size and ionization energy, and less about electronegativity, because I'm more likely to ask about one of those two. All right. Oxidation states. Here's a fun little chart showing the common oxidation states. These are not all possible oxidation states, but these are the most common that we're going to see. In fact, they're broken into two sections. In the light red, you have the most common, the most stable oxidation states. You find these all over the place in natural occurrence. And then you have the dark red ones, which are certainly made in nature. We can certainly find them out there. They're not hard to make in the lab, but they're just less common. They're not as stable as the more common ones, right? The more stable things are, the more common they are. So what do you see as a trend here in this chart? Well, as a trend here in this chart, I see this very distinct line at the very beginning going up, right? I see this light red line saying that as I go from scandium to titanium to vanadium to chromium, the most common oxidation state, +3 for scandium. If you go look back at the periodic table, a +3 for scandium means I have lost both the 4s electrons and my 1 3d electrons. Titanium is +4. That means I've lost both my 4s electrons and both of my 3d electrons. Vanadium, +5, means I've lost both 4s electrons, all 3 of my 3d electrons. So you can see for the first half of the periodic table, for the first half of my transition metals, the most common oxidation state is for it to lose every single electron in the 4s and the 3d. So what does that say? It says that these guys are willing to lose those electrons because they must not be holding on to them too tightly. Okay? They're willing to lose them because there's going to be some energetic gain of making that ion. They're going to pair with something, either an anion or with water, something very polar, in order to make up that energy loss. All right, so it loses all of its electrons. But as soon as you hit that halfway point on the periodic table and you get down to iron, boom, you don't see iron 8+. You just don't. You don't even see iron 7+. In fact, the most common oxidation state of iron is then iron 2+ or iron 3+. And that trend goes across the periodic table from iron all the way over to the zinc, that the most common oxidation states are +2. What is +2? Remember, when we're removing electrons, we're going to move the 4s first. And so all of these +2 oxidation states mean that your transition metal has a configuration of 4s0. You've taken away the 4s electrons. So here we're holding on a little tighter to our 3d electrons and a little less tight to our 4s electrons, and those are the easier ones to remove. Why is that? Well, as you get towards the right-hand side, what do we see? We see increasing atomic charge, right? So you have more protons pulling on those electrons, makes them a little harder to remove. But also, if you think about trying to remove all the electrons from zinc, you'd have to have a +11 charge. You're trying to take electrons away from something that's already got a +10 charge. That just doesn't happen. It's really hard to do. The more positive you are, the more it's going to resist losing that next electron. In the first half of the periodic table, there was enough energy gain in order to make that worthwhile. But at the end half of the periodic table and half of the transition metals, there's just not enough energy gain. And again, you might not know that until I show you this data. So don't be like, was I supposed to come up with that all on my own? No, what we're trying to do is we're trying to take existing data, this chart that's in front of us, and explain why might this chart be true. And that's what we're doing. I don't expect you to be like, I should have known that off the top of my head. No, you shouldn't have. But you should be able to explain it when you see it, right? And that's what we're trying to do. Interesting one over here. Why is copper the only one there with a +1 charge? And not only that, a common +1 charge. Well, if you remember, copper borrows 1 from the 4s and has a configuration of 4s1 3d10. That completely filled d orbital, very stable. You're not as likely to lose an electron from it. And so you end up losing just your 4s electron and having a +1 oxidation state. However, chromium, even though it does the same thing, doesn't have that same difference. It doesn't have a +1 oxidation state. And in a homework problem that you might do, I ask you, why do you think that is? And so it's something worth trying to ponder, is why chromium doesn't have a common +1 oxidation state, but copper does, even though they both have a configuration of 4s1. All right, we're going to jump from periodic trends over to talking about ligands. Now, what is a ligand? A ligand is anything bonded to a metal center. So if I take iron and I've got an iron 3+ here and I start to bind things to it, let me take a CN I bind cyanide to it, or if I take water and I bind the water to it. Those are ligands. They are bonded by covalent type of bonds to, they're actually specifically called coordination covalent bonds, but they're bonded by essentially covalent bonds, sharing of electrons, and to this metal center. And so we're going to talk about next is a bunch of things related to metal centers and ligands, and a bunch of language and ideas associated with that. So first we needed to know what a ligand was. The next thing we need to know is what's the difference between an isomer and a conformer. So it turns out there's many ways of arranging atoms or groups around a central atom. And I've got a few drawings down there, and it's going to kind of give you an idea of what I mean. And there's a difference between rotating the molecule. So in that first molecule, I have kind of 3 carbons attached to each other. And that's going to be the main part, where when we get into organic chemistry, we'll call that the backbone. That's the main part of the molecule, and then there's a bunch of hydrogens around. There's also a bromine around right there. And you can see he's sitting on top. Now, all of these carbon-carbon bonds are single bonds. And if you were to go make yourself a molecular model of this, and I totally forgot to do it ahead of time for this, if you were to make yourself a molecular model, what you'd find is that when you have a carbon-carbon single bond, you can rotate around that thing pretty easily. So let me, this is not the molecule we're looking for, but I've got this molecule right here. And when you have a carbon-carbon single bond, these 2 black ones, what you find is that all these other things can rotate around that fairly easily. In fact, I can rotate all these things and get very complicated rotations, but this is almost 0 energy. It's really, really easy to rotate this guy around. And so what turns out is that molecules are constantly rotating and vibrating and changing shape and all those kind of things. So this guy can very easily rotate. And let's say my bromine was this one that's not marked on this one I just happened to find on my desk. And we turn that around, and all of a sudden the bromine's on the bottom. But there's really no difference. We're just kind of rotating around that bond. And we end up with something that looks like that. So we can draw either of those, and they're pretty much the same molecule. There's no difference between them, because it turns out the molecule is constantly rotating like that anyway. And we call those conformers. Conformers are, I'm rotating a molecule around single bonds in the molecule. Now, double bonds and triple bonds, you don't rotate around those, because you remember, double bonds, you have these pi orbitals connecting, and it kind of locks in the molecule. But a single bond, it's sigma. It's straight in the middle and rotating around it. Really, really easy to do. So those are called conformers. But we're going to talk mainly about these things called isomers. Now, what's an isomer? An isomer, in order to make an isomer of a compound, so we have our first compound here, same one as we had above, the bromine's on top there. We rotated it before to get the conformer, where the bromine was just down, but now we're going to make an isomer. And in order to make an isomer, you have to break a bond and make a bond, at least one. Okay? We're going to break a bond and make a bond. So what are we going to do? We're going to break this bromine off of here. We're going to break this hydrogen off of here, and we're going to switch the 2. The only way to do that is to break those bonds. Right? If I just moved the bromine to the bottom in my conformer, I could do that by rotating. But I can't move this guy over here, this unlabeled one for my bromine, over to here without breaking it, swapping them around. Okay, and you have to make those noises too while you're doing it, because it really, really helps. All right, so you got to break a couple bonds, make a couple bonds. That is an isomer. I've got the exact same things. I've got the 3 carbons, I've got all the hydrogens I have, the 1 bromine, but I've rearranged them in such a way that they are connected differently. Okay, same chemical formula, but different arrangement to the molecules, more than just rotating a bond. Breaking a bond, making a bond. That is an isomer. So it turns out there's many different ways of forming isomers. There are structural isomers and stereoisomers and coordination isomers and linkage isomers and geometric isomers, optical isomers. I feel like we're in Kansas or something. Oh my. So what we're going to talk about is a bunch of these different ones. The stereoisomers, especially the optical isomers, we're going to cover that here. We're going to really go into that when we talk about organic chemistry. But these are the different things that we're going to talk about. Now, we're mainly going to focus on this level down here, which are the specific types of isomers. But we should know this level up here that covers those ones, and we'll see that as we go along. So structural isomers, they have different connectivities, and stereoisomers have different connectivities, right? But we're going to see there's this very specific thing about stereoisomers that talk about spatial arrangement. All right, so I got a picture down here, and I want to know, do I have a picture of an isomer, or do I have a picture of a conformer? And I'll just go ahead and rotate. Ow. Ooh, ooh, go. OK. I gave you a hint. Did you notice what the hint was? I said, I'm just going to I don't know if you picked up on it. All right, what do I have? It turns out I have a conformer here. Okay, because all I did is rotate this fluorine down to the bottom. I can do that just kind of by rotating the molecule around and moving my fluorine around. I didn't actually have to break a bond and make a bond. There's all single bonds between those carbons, so I can rotate freely around them. So I had a conformer here. If I'd moved the fluorine over here or over here, that would have been an isomer. All right. So we've now talked about isomers versus conformers. Now we're going to mainly focus on isomers. We're going to break apart bonds, move things around. Complex ions versus coordination compounds. We talked about complex ion formation. What did we have when we had complex ion formation? The complex ion was the metal plus the ligands. And the important part is it was a charged compound. It was a charged compound. So when we made things like cobalt with 6 ammonias around it, we had the metal, which was cobalt plus 2 or plus 3. We put the 6 ammonias around it, and what we had was a complex ion, which was the cobalt complexed with those 6 ammonia ligands, and the overall thing had a plus 2 charge. What we have now is we're going to talk about coordination compounds, which is a superset of complex ions. Because what it is it's a complex ion plus the counter ions. So if complex ions are charged, nature never just has charged things floating around all by itself. It always has to come from somewhere, right? If cobalt's plus 2, that means it lost 2 electrons. Those 2 electrons had to go somewhere and balance out things in the world. So when we talk about a coordination compound, we're going to take that complex ion. In this case down here, we drew something with a cobalt 3+. And we're going to have counter ions that counter that 3+ charge. So we have an overall charge of 0. So in a case of cobalt 3+ down here, coordinated with 6 ammonia molecules, in order to counter that charge of my coordination or my complex ion, which is the thing shown in the blue and the white in here, I'm going to need 3 chloride ions, which are the green ones here, kind of mashed around it in order to cancel that out, right? And if I make the complex ion, that can be dissolved in solution because it's ionic, in fact only occurs in solution. But as soon as I make the coordination compound, that is more likely going to be a solid because I'm now not charged. But here's a funny thing. Once we make this whole thing called the coordination compound that's got all parts, the cobalt and the ammonia and the counter ions, I can do funny things to it. I can start switching out my ligands, the things attached to the cobalt, with my counter ions. And all of a sudden now, I can take one of these counter ions, like say this one, and I'm going to attach it here. I'm going to make an isomer. I'm going to remove the ammonia, and I'm going to attach the chloride, and I get, let me make sure to circle that well, I get this part as my main complex ion now. I've got cobalt with 5 ammonia, but now I've got a chloride actually bonded here to my cobalt center, and so I've got a different molecule. I've got a different molecule. This is a coordination compound that has only 2 counter ions. Now, if we look back over here to our flow chart here, what is that? It's called a coordination isomer. The ligand and the counter ions are changing places. So these 2 things here are called coordination isomers. We are trading out a ligand for a counterion in a coordination compound. Lots and lots of language to keep track of, but it's important to try to keep track of these things and talk about them accurately. All right. Turns out there's more we can do. We could do this again. We could take a second one of my chloride ions, remove a second ammonia. It floats off. It's kind of neutral, so it's not going to participate in our thing. It's not needed as a counterion. And now I've got two chlorides attached there. So the main part of the name has the two chlorides in it. Then I stick that counterion chloride on the outside of those brackets there to say the things in brackets, the square brackets, that is my complex ion. The whole thing together is my coordination compound. And remember, coordination compound is always going to sum up to a total charge of 0. If you don't have a total charge of 0, you still have essentially a complex ion because you haven't neutralized and balanced all your charges. So it turns out these two are also coordination isomers because I have moved things around. Even the first one and the last one would be considered coordination isomers because I have broken more bonds and moved things around. Generally, isomers, you try to do kind of one or two things at a time, but that's not required at all. It's very common still to see isomers where you're breaking multiple bonds and moving multiple things around at the same time. So you should be able to identify coordination isomers by looking at pictures and being like, hey, look, a ligand broke off, a counterion came in, or looking at those formulas and seeing the same thing. All right, next thing, let's talk a little bit about some of the language associated with these coordination compounds or the complex ions. Here we've got a metal center and it's coordinated. You can see this little octahedral configuration. Remember when there's 6 things attached, we call it an octahedral configuration. And that's very interesting. So we've got one metal attached to 6 different things. But if you look very carefully, those 6 different things are all on the same molecule. Very, very interesting. So you've got one metal center attaching 6 times to a single molecule. Now, it's only possible if that molecule is big enough to be able to wrap around the metal and have all sorts of different places that the metal wants to bind to. Where does the metal want to bind to? It wants to bind to things that are slightly negative or completely negative. Why? Because it's positive, right? You're not going to bind to something positive because they're going to repel each other. And so we've got all these kind of negative spots on this molecule. Remember, nitrogen is fairly high in electronegativity, so it's going to be drawing electrons to itself, going to be slightly negative. But all these negative parts here, we're going to be attaching and binding to those negative parts and forming my little coordinate covalent bonds. But not everything can do that, right? Water, if you look at water, right, it can only bond once to a metal. It's going to bond with that oxygen there because that oxygen is slightly negative. And it can't bond to those 2 pairs at the same time. The geometry just doesn't work out. And so things like water, you can only bond it one time. But things like this bottom one, which is the one also shown here in this picture, which is called EDTA, ethylene diamine tetraacetate, which you'll see on labels all the time in food. It's a food preservative, which we'll talk about in just a second. You eat this stuff, okay, just so you know. So EDTA can coordinate 6 times with the same molecule, and that's really, really cool. So it turns out there's language that's associated with that. Things that can bind several times, or actually let's start with one. Things that can bind only once, things like water, ammonia, chloride, carbon monoxide, cyanide, thiocyanate. They can only bond one at a time, just because they're not big enough to wrap around and be able to bond in 2 different spots, or they just don't have 2 different binding sites that the metal can get to. Those are called monodentate. Now, dentate, what is dent, right? It has to do with teeth. And so what we're saying is that these guys can only bite into the metal once. We call them monodentate. Then there's slightly bigger molecules that can actually wrap around and get a little bit around the metal, maybe twice, and we call those bidentate. Okay. So those are bidentate. They can bind twice. Those are things like the oxalate ion. So if you go back to our complex ion formation tables in the back of the textbook and look at those tables, there's a bunch of things that said parentheses OX. And that's just short for the oxalate ion, so you don't have to write out that formula. Or there's a bunch of things that said parentheses EN, and that's short for ethylene diamine, which again is a somewhat complicated molecule to write out. But those are bidentate ligands. Each one of those can coordinate twice to the same metal center. Then, if you can coordinate 6 times like an EDTA, you might think, oh, you know, six, no, we just call it polydentate. Polydentate means it can do it many, many times. So EDTA, ethylene diamine tetraacetate, is a polydentate ligand. It can combine 6 times to the same metal center. Now, think about how well these are going to connect. If I've got a water molecule and it's connecting to my metal center in just one bond, right, it's going to require a certain amount of energy to pull that thing off. But if I've got an EDTA and it's bonded here, and it's bonded here, and it's bonded here, and it's bonded here, and it's bonded here in an octahedral configuration, let's say I want to remove that thing and I start trying to peel off the EDTA. So I get this corner off, and that takes, you know, about the same energy maybe as it took to get the water off. All right, and then I got to grab another hand and I got to pull this over here. This goes, reconnects while I'm trying to get the side off. I mean, you've probably tried to do this before, right? If you ever tried to get a toddler away from something they really want, as soon as you grab one arm, the other leg wraps around, okay? So you let go of that arm to get the leg and the arm wraps, right? That's what the EDTA is doing. It's wrapped around that metal. It can wrap that metal really, really tightly and not let go. And that's why EDTA is actually used as a food preservative, because it goes and finds metals in there, wraps around them, and essentially makes those metals unavailable for bacteria and other things to use. Bacteria and all cells need a little bit of metal here and there in order to operate and grow and things like that. But by essentially inactivating those metals, by coordinating around them really, really tightly, the EDTA can mess up that. Now, is it going to mess you up? No, unless you're drinking gallons of this stuff, there's not enough to mess you up because you've got a ton of metals in your system. You're not going to mess yourself up by just having a little bit of EDTA in the food. It's just there to prevent bacterial growth. So monodentate once, bidentate twice, polydentate many times, as many as 6. You don't end up generally finding things more than 6. 6 is kind of the limit. And you can see my little dog there is a polydentate animal. Many teeth. All right, the next thing we're going to talk about is linkage isomers. And linkage isomers are very, very interesting. I'm going to blow this guy up on the left here. And what do we have? We have cobalt with a bunch of ammonias around it. Those are each ammonia here. But down here, I have got an NO2. NO2 looks like that. There's a double bond on one side. But in this one on the left, the cobalt is actually attached to the nitrogen, right? If you remember your electronegativity series, FOClN, nitrogen is electronegative, but it's not as electronegative as oxygen. So these guys are actually slightly negative charged. And this guy's actually slightly positive charged, but it's still good enough that the cobalt can attach to it. However, if you do it right, you can also change the chemistry. And instead of having the cobalt attached to the nitrogen, you can make the cobalt attach to the oxygen instead. So where it's linking, where it's attached to the ligand, even though it's the exact same ligand, it's NO2, you can actually do some chemistry to force it to attach either to the nitrogen or to the oxygen. And what's really cool is you actually get different chemistry. Just here you can see color. There's a yellow one here and an orange one here. The yellow one comes when you are attached by the nitrogen. The orange one comes when you are attached by the oxygen. And so here we have the exact same thing attached, the exact same complex attached to the exact same ligand, but in a different location. And we call these linkage isomers. And they really only occur with ligands where there's several elements in there that tend to be somewhat electronegative or have lone pairs on them, right? What we're really attaching to here is the lone pairs on that nitrogen, because nitrogen always ends up with lone pairs on it when you do the bonding. Pretty neat. All right, coordination isomers. What about coordination isomers? Did we already talk about that? We talked about trading out our ligands and our counter ions, and that's again what we're doing here, coordination isomers. I've got the chlorine here, and I've got the bromine on the outside of those brackets as my counter ion. How do I know the difference between them? Because there's a bond drawn between that chlorine and the cobalt, so I know it's a ligand, whereas this guy's just kind of floating out there, so I know it's a counter ion. I swap those, I get the bromine attached, I get the chloride. Again, those are going to have different chemical properties, and we call those coordination isomers. More coordination isomers. Here we've got one where we've got 6 waters attached to a chromium, and then we trade out. We've got 3 chlorines on the outside. We trade out, we've got 2 chlorines on the outside, and now we bond one of them. There is an extra water there. We don't worry too much about it because it's not participating in the charge balance, but it is out there. And now we've got the chloride in there. And so we can say, hey, we've got a coordination isomer there. Coordination isomer trading out a ligand and a counter ion. Linkage isomer is bonding to the same molecule but in a different spot. So ligand attaches nitrogen versus oxygen, or sulfur versus nitrogen, depending on the molecule. Geometric or stereoisomers. Here's some fun ones. Let's go ahead and look up here. And we've got this platinum complex. It's got 2 ammonias and 2 chlorides. It forms this square planar configuration. And so you can set it up where the ammonias are on one side and the chlorides are on the other. Or it turns out if you do some different chemistry, you can force those chlorides to be across from each other and the ammonias to be across from each other. And when we go across, we call it trans. Trans means across. Transatlantic ocean means you're going across the Atlantic Ocean. And when they're together, we call it cis. Cis means on the same side. So here we call it cis because the chlorides are on the same side. You can also say the ammonias are on the same side. And so we call that the cis isomer. And we call this one over here the trans isomer. You've probably seen this before when you talked about cis and trans bonds, when you talked about double bonds, when you first learned about the bonding in there. But really neat in that the chemistry of these is very, very different. In this cis versus trans platinum complex here, one of them is a very active anti-cancer agent. I think it's the cis platinum. But one of them does nothing, which is, I believe, the trans one. Don't quote me on it, but I'm pretty sure. Okay. So that's really neat. Just by rearranging these guys, exact same things, exact same configuration, one of them helps fight cancer, one of them does nothing. Really, really cool. All right. We can also do that in octahedral complexes where there's 6 things attached. We can have the cobalts or the chlorides there next to each other. It doesn't matter. These could be chlorides, these could be water, but right, the 2 things that are different are next to each other versus the 2 things that are different are across from each other. When they're next to each other, we call it the cis isomer. When they're across from each other, we call it the trans isomer. And you should be able to identify those if I give you pictures of them similar to something that looks like this. Across, trans, next to each other, cis. What happens if I have 3 and 3? So this is 2 and 4. I've got 2 chlorides and 4 ammonias. What happens if I have 3 and 3? Well, it turns out when you have 3 and 3, there's a couple different ways of arranging it. One is where those 3 are kind of right next to each other, and they form kind of an arm, right? If you think about something like this, you've got this top part, those 3 kind of facing that way. And then they can also form a plane. Now, I can't draw in 3D, but you could kind of imagine that these 3 ones here kind of form a flat plane. And what's the difference between those? We don't call them cis and trans anymore because we've got 3 things, like across from what? So what we do is we call them FAC and MER. Now, FAC and MER, you're like, that totally sounds random if you don't know what they mean. But FAC means facial. And why facial? Because if you draw a little triangle here, what you've actually just drawn is the face of the octahedron, one of the faces of the octahedron, by drawing those 3 and connecting them together. And that's why we call it FAC. It stands for facial. But here, if you draw a triangle between them, it doesn't form the face. It's actually kind of the middle of the molecule, and it kind of bisects the molecule, actually. And we call something, a line that bisects something, the meridian. And so this is actually facial and meridian, and that's where it comes from. But people just call them the FAC and the MER. So FAC, one side, all 3 things attached on one side. MER is, it kind of forms a plane in the middle of the molecule, dividing the molecule in half, and we call that the meridian. So you should be able to identify these geometric isomers, which fell under the category of stereoisomers, as geometric isomers, and as trans, cis, or as facial and meridian. Facial and meridian only if you've got 3 and 3. Trans and cis if you've got essentially 4 and 2. You could totally have this guy here be a bromine and this one still be a chlorine, and that you could still call a cis isomer. That's fine. But if you start having too many things around, like if you try to have a chlorine and a bromine and an ammonia and water, you lose that symmetry that you need in order to talk about cis and trans. And there's other ways of talking about that. All right, optical isomers. This is my favorite one because it's really, really funny to think about. What is an optical isomer? Okay, so an optical isomer are what we call chiral molecules. And I'm going to tell you how to identify them first, and then we're going to talk about them. How can you identify an optical isomer? Is you have a central atom, and this can be a metal, this can be carbon, okay, with 4 different attachments. And there's other little rules and things like that, but that's how we're going to identify these things. And we call them optical isomers because they actually do funny things to light, and we'll talk more about that in detail in the organic chapter. We're just kind of brushing the surface here, and we'll brush a little harder in the organic chapter, but not too much here. So optical isomers are what we call chiral molecules, and it's a central atom with 4 different attachments. Now, in order to talk about this, what we're going to do is we're going to make a carbon here, and I'm going to attach 4 different things to it. So if we draw A, B, D, and E. Now, if we want to be really careful, we've got to make sure that we are drawing our kind of 3D things here, because when we have a tetrahedron, we've got to make sure that our tetrahedron has the right shape. So if we look at our tetrahedron, if this was my A and my B, those are going up, then my E, D, and E, one coming in, one going out. If you remember your drawing, this is the one that's going away from you. So in this case, it would be the one that's behind this guy here. And this E is the one coming out, and that's the one going towards you. So that's what I just drew here, is if we had A, B, C, and D, I'm sorry, A, B, D, and E here attached to carbon. Now, it turns out that we can take this molecule, and because it's got 4 different things, we can just swap out. So I'm going to draw it without, well, let me draw it with the colors. We can just swap out our same carbon here, swap out the A and the B, like that. All I did is switch those. The D and the E. And it turns out that is a different molecule. And it doesn't look like it at first. You're like, that looks pretty much the same to me, Professor Clements. But it turns out, if you try to put these on top of each other, they're not the same, right? And unfortunately, I forgot to prepare ahead of time here. So let me see if I can do this real quickly while I talk. I forgot to make my little molecules as I went along. So I'm going to kind of fake this here with what I just happen to have on my desk, so I don't have to take too much of your time listening to my things go pop, because that's not fun for you. Right, so I'm almost there. I've got, wow, the thing does not want to go on. There we go. I've got 3 different colors. Now I just need 1 more central atom to get me my 4 different colors. All right. There we go. So now I've got my 4 different colors. All right, I've got my 4 different colors. So if I take this guy and I swap these guys, right, I can't just rotate it, because look what happened. When I had it like this, when I had the A on one side, the B on the other, this white one was in front. If I just rotate it, the white one is now in back. And there's no way to get these guys to rotate without ending up swapping the one in the front and the one in the back. So it says that these molecules are not the same. All we did is change the location of those two things. So we have this situation, right? We have 4 different things attached, A, B, C, A, B, D, and E attached to my carbon, and we end up with what we call our optical isomers or chiromolecules. Why do we care about these? We care about these because they have so many interesting properties. The properties of the one on the left are going to be very different than the properties of the one on the right, and we're going to see examples of that, especially in the organic chapter. What else do I want to say about that? Also, a lot of biological chemistry depends on these stereoisomers, these optical isomers of slightly different arrangements. One way it works, one way it does nothing. And again, we'll see a lot more examples of that as we go into the organic chapter. So, what kind of stereoisomers can we look at? We can look at all sorts of stereoisomers. It turns out you can look at coordination or at metal centers with things attached to it and rotate them around. Now, one of the things that people will say is that if you take this one on the left and you take its mirror image, right, then it's not going to be superimposable on the starting one. And that's kind of what I did here, is I took a mirror image of it and they weren't the same molecule. So again, we'll delve into that a little more in the organic chapter, so don't worry too much about that language for this chapter. Okay. But it says, hey, look, if I take this guy, I take his mirror image, they are no longer the same. It's a little hard to see here. This little ribbon that you see between these ones are because we've got bidentate ligands, so they're actually the same molecule attached there. And it turns out when you put this into a mirror and rotate it around, they are different molecules. And so you can get stereoisomers that way. You can get stereoisomers this way. We're going to talk a little bit more about this one in the organic chapter. You're going to hear that several times because it's really important in organic. But this guy is a stereocenter is what we call it. For those who haven't seen this kind of structure drawing before, this point right there in the middle is a carbon atom. Okay, so we've got a carbon with a hydrogen, some other carbons, some funny carbons there, and some different funny carbons there, 4 different things attached. Even though it doesn't look like it, you're like, oh, they're all attached to carbon. It turns out you can look pretty far out. But anyway, don't worry about that till the next chapter. What's really cool is you take that molecule, you rotate it around, you take the mirror image, and you get a very, very different molecule. One smells like spearmint, that very, very intense spearmint flavor. The other one smells a little more like fennel. And if you've ever smelled fennel, it's a very subtle smell, somewhat like licorice. Very, very different. Same thing down here. We've got a carbon with 4 different things attached. That's kind of what I was showing you here. So stereoisomers identified primarily by having 4 different things attached, but there's also other cases here where we've got metal centers with these ligands. I'm probably not going to ask you too much about those because those are hard to see. Those are really, really hard to see without models and really kind of delving into them. But we're going to do lots of ones that look something like this. All right. So again, back to isomers. What do we have here? We have cis and trans. What do we call the cis and the trans? We call those geometric isomers, not stereoisomers, not optical isomers. Why? Because there's not 4 different things attached. There's actually only 2 different things attached. But in one case, they're next to each other, cis, and in the other case, they're across from each other, the trans. Here, you can see we've got 3 things attached, the chlorine, chlorine, chlorine on my cobalt center. That's a facial one because they're next to each other. Here, it's going across the middle, and so we call that meridian of that cobalt complex. And then also, like I said, these ones with the metal centers, with the bidentate ligands, very difficult to see without actually having a model in front of you, but those are also optical isomers or stereoisomers. Okay, so what is your job in all this? We went over a lot of language. Okay, I want you to be able to identify isomers by looking at pictures of them, essentially. Okay, so you can be able to identify a coordination isomer. What's a coordination isomer? You're swapping out a ligand for a counter ion. So you need to have ligands and counter ions present in order to have a coordination isomer. A linkage isomer, you're attaching the same thing but in a different spot. One's attached to the nitrogen, another one is attached to the sulfur. Geometric isomer, you will have the cis trans or the facial and meridian. So you're looking at something that's square, planar, two things on one side, or versus those two things across from each other. Or you're looking at an octahedral one where three things form a facial, one of the sides of the octahedron, or meridian, it kind of carves the thing in half. And you should also identify optical isomers. The most common one we're going to see is something with 4 different things attached to it. Again, we're going to go much more into the detail on that in the organic chapter. You're going to be tested on these at the same time, so you're going to have that knowledge of the organic chapter when you are talking about trying to identify optical isomers. You should be able to write electron configurations for transition metal ions, and you should be able to explain trends in transition metal size, ionization energy, and electronegativity, not so much. Okay, but remember, if it's not charge, it's size. If it's not size, it's charge. Okay, I know this has been a long time. This is one of my longer videos. I didn't split it up well, but let's just check in one more time here. We're going to identify the type of isomer shown in the picture. Is it a coordination isomer, a linkage isomer, a geometric isomer, or an optical isomer? Now I got to tell you, I look at this thing and I'm like, wow, I didn't draw that very well, but that's okay because I didn't draw it. But you can still see what's going on. In both cases, there's 2 chlorines there. And right, we don't have the counter ions present to show that there are counter ions, so maybe these guys are just floating around in solution. So go ahead and try to identify the type of isomer. What did you come up with? Well, what do we have? We've got the chlorines across from each other there, next to each other there. That is a geometric isomer. It's not like we have these bidentate ligands attached funny for our optical isomers. It's not like we're attaching at a different spot on the chlorine because it's just a chlorine. So it's not a linkage isomers. And it's not a coordination compound because we didn't talk about taking like a bromine counter ion out here and then swapping it out. We didn't do that. And so it's not a coordination isomer. And it leaves us a geometric isomer. And this right over here was the trans version, and this over here is the cis version. All right, we're finally done. Sorry for that extraordinarily long video. I did not intend for it to be this long, but that's just kind of what I came up with. Have a wonderful day, and we will talk some more later.